don't have that background, I'll try to fill in. But if you don't understand something I'm saying, do not hesitate to stop me and say so, okay? I much prefer that. I think conversations are much more interesting than lectures as a general rule. So I'll try to abide by that. So let me preface the talk by saying that this talk is about cyclones, broadly writ. Okay, what is a cyclone? It's what we usually think of as a storm, like the rain you're about to have. Here in Perugia comes from something called a baroclinic cyclone, which is the most common kind. And those cyclones are powered by the fact that there are horizontal temperature gradients on surfaces of constant pressure. Normally those temperature gradients can't be sustained because they're equalized very quickly, but in a rotating world they can be, but that balance state is unstable in very interesting ways. And most of what we call weather on the planet outside the tropics is powered by that. But there's a different kind of storm, the prototype of which is a hurricane, which has an entirely different, completely separate energy source. And that energy source results from the fact that we live in a greenhouse world, which I'll be talking about in my next lecture. And what it means is that the sunlight absorbed by the oceans is not mostly balanced by infrared radiation in space, which would be the case if we did not have greenhouse gases, but is instead balanced by evaporation of water, which is a big heat sink for the ocean and a source of the atmosphere. To have all that evaporation, you have to have an evaporative potential. And that's reflected in the fact that the humidity of the air just above the water is not saturated. So you have this disequilibrium, thermodynamic disequilibrium. And in many, many different systems, including biological systems, when you have enough thermodynamic disequilibrium, that fosters organization. And a hurricane is an example of such an organization. And we've come to understand hurricanes much better because we understood the simple fact. The hurricanes make use of and draw their energy from this thermodynamic disequilibrium. And the more greenhouse gas you put in the atmosphere, the more disequilibrium there is, and so you can have stronger hurricanes. But today, I want to talk about a kind of storm which is somewhat in between those two storms. And they include storms that sometimes happen in the Mediterranean, which some people have called, including myself, are called medicanes, a word I don't particularly like, because it's combining all kinds of different languages in an awkward way, but that's life, we have medicanes. But we've come to realize that medicanes and other kinds of storms, similar storms in other parts of the world, are basically all the same phenomenon. And so at a meeting this past summer in Paris, a group of us, you can see their names at the bottom of this title slide, spent days arguing, mostly over wine, about what we should do about this, and we came up with an acronym, Cyclops, borrowing from Greek mythology, but it's an acronym that stands for cyclones from locally originating potential intensity. Now that won't mean anything to a lot of you, but I have fun to describe it. So we're trying to unify storms all over the world of a particular type that all have the same physics, basically. So these storms are, I call this a rogues gallery of storms, polar lows. These are storms that occur, interestingly enough, in very high latitudes in the middle of winter. And yet, they're the same as the storms that occur in the opposite climate, the tropics in the middle of the summer. How can that be? They're very hurricane-like. They have eyes. They arise quickly. They take fishing vessels by surprise with tragic consequences. Medicanes, which I just talked about, here's a picture of one. They look like miniature hurricanes. They occur in the Mediterranean, as their name would imply. Subtropical cyclones, which is an amorphous term. It's not an official term, but forecasters use this a lot to describe this phenomenon in places like the North Atlantic. And then we have coma storms, christened by Hawaiian meteorologists, for storms they think are peculiar to Hawaii. So these turn out, not too surprisingly, to be all the same creature, from a physical point of view when we're coming up with this word Cyclops to unify it. So the hypothesis is that these storms, like hurricanes, are all powered by surface enthalpy fluxes. But they occur outside the place where this potential is normally high. And we actually have a way of quantifying that thermodynamic disequilibrium potential, the quantity called potential intensity. And it just comes from a direct application of Carnot's famous theorem to this quantitatively, a measure of this thermodynamic disequilibrium. If you see PI in this law, it's not principal investigator, it's potential intensity. And I should have brought a cartoon to show you what it is, but I didn't. It has the units of velocity, and it can be shown to be upper bound on the surface wind speed you can have in a cyclone that's powered by surface fluxes. It works very well for hurricanes. That is, if you normalize the wind speeds in hurricanes by this number, which varies from place to place and time to time, you get a universal probability distribution. So you know you've kind of normalized it by the right number that way. So potential intensity is useful, and people use it a lot, as Paulina mentioned, in tropical hurricanes. But we also think that these storms that I was talking about that occur at high altitudes, and are fairly unusual, by the way, are also powered by the same mechanism. So the difference is, if you look at the climatology of the tropics in their respective warm seasons, there's always a lot of potential intensity. Hurricanes are rare, but their occurrence is not limited by this potential. Okay, there are other things that limit them, which we can talk about later if you like. Whereas the Rhodes Gallery, I can show you, of medicanes and polaroids occur at places and times of the year where almost always there's no potential at all. But that potential can arise temporarily and locally from large-scale dynamical processes in the atmosphere. And that's the realization of that makes these storms a little bit different from a theoretical point of view than they're tropical. Because once they're formed, they're really identical to tropical cyclones, but the way they arose is different. So the idea is that pockets of this high potential arise locally in space and time from something called cold core upper tropospheric cyclones. That's a technical term, some of you recognize, some of you don't. But basically, you're taking the kinetic energy of the jet stream at high altitudes and locally turning it into potential energy. That is, you're lifting cold air, if you will. You're creating potential energy at the expense of kinetic energy. That cold air is cold relative, it can be cold relative to the underlying sea, and that locally creates this potential. It may last a few days, and it may cover an area of 1,000 kilometers squared. And it doesn't, as I say, it vanishes after a while, but it can last long enough to locally create what amounts to a hurricane. That's the idea, and I'm going to show you evidence for that. So surface flux, what we call surface flux-driven cyclones, another term for the thing that's powered by this disequilibrium. We christened this name Cyclops, just so that we could remember it, basically. Locally originating potential is the key here. So this is a cartoon, a series of 3 cartoons meant to show this, and this is going to be a little tough for non-people without atmospheric science backgrounds. I don't know if we've got a pointer. Can you see that? No.
I think there is a pointer.
This is a cross-section through one of these upper-level cutoff cyclones. The black lines are isotropes. For those of you who are in meteorology, potential temperature is increasing with altitude more rapidly in the upper troposphere. And where these plus of entropy bend upward, the air is locally cold. So the gray shading, again using a term that's peculiar to meteorology, is called potential vorticity, which is a very, very interesting quantity of shading there. You have a forms a meander, sometimes an oxbow lake. It's just like that. It happens much faster in the atmosphere. And there are a lot more dynamics involved. So you can create a pocket of very cold air in the troposphere. This is up, but we're using pressure as a proxy for altitude here, which is another thing we often do. And I should have put it on here. This whole diagram is roughly 500 kilometers apart. In the particular scenario I'm showing here, this cold air, or this cutoff cyclone occurs over the land, which is the green, and then subsequently moves out over the water. The red contours are contours of the axisymmetric component of wind in this plane. These systems are rarely axisymmetric. Think of it as a cross-section. And this is the wind normal cross-section, but it's one side on one side of the diagram and the other side on the other side. So if we wait a day or so, this is simply the detected bodily moves out over the ocean. The ocean doesn't have to be warm from the point of view of conventional ideas of ocean temperature, but it's warm relative to the air. That's what's important. And it's in this pocket of cold air, it's strongly out of equilibrium with the ocean surface. And you begin to have surface winds. These isotachs are now intersecting the ocean surface. Once you start to get a cyclonic circulation at the surface, a very important feedback kicks in, which is active in all these storms, which is a feedback between wind and flux, surface heat flux. Everybody's had that experience. If you're outside on a day like today, and the wind starts to blow, you feel colder. Why? The evaporation and heat flux from your skin is going up. And why is that? Because the rate limiter, right, it's not just molecular diffusion, otherwise it wouldn't matter. It's turbulence near your skin that's actually the rate limiter of taking heat away. So when it's windier, there's more turbulence, you have more flux, you feel colder. Right? Particularly if you're wet, because it's a very efficient way of doing this, is evaporating water. It's exactly that over the ocean surface. The rate limiter in getting heat out of the ocean under these conditions of disequilibrium is small-scale turbulence generated by wind flowing over the water. That's all. The windier it is, the more heat flux. But it's the heat flux that's powering the storm. So if you have more heat flux, the storm gets stronger, the wind gets stronger, and you have more flux. And that will go all the way up until the air column in the center has warmed up sufficiently that there is no longer any thermodynamic disequilibrium in the water. That's where the idea of potential intensity arises. Calculate that. How strong does the system have to be to shut down that thermodynamic disequilibrium? So this is the third phase where you have a mature cyclone, not just in the upper troposphere, but at the surface, these isoclasts of wind right down to the sea surface. You have a strong cyclone. They're different from the kinds of everyday low-pressure systems you see on weather maps. They can be very concentrated and usually stronger in terms of wind. And they develop much faster, so they catch weather forecasters off guard. So from a practical standpoint, there's also some interest in understanding these things. The problem in calculating the potential intensity under these cutoff flows is that in practice, this doesn't happen in quantized segments like I just showed you. That's just a simplification. It all happens about the same time. And as soon as you start getting any circulation at the surface, the column warms up. And now the potential density goes down, but you really want to know what was the potential before that happened. So there's a trick, and I'm not going to derive it because it would take some part of the seminar to do that. But on the left-hand side, and I'm showing you the modification, is the square of this modified potential intensity. So wind speed squared. It's meant to be the estimate of the strongest wind you can have in a cyclone. On the right-hand side is the conventional potential intensity one would just calculate the way one normally does from an analysis of the ocean temperature and the atmospheric temperature. And from the added term has a bunch of factors which You don't need to worry about whether you're all multiplying this phi prime. It's the perturbation to the low-level geopotential from the cyclonic storm itself. Look at it as surface pressure perturbation. Surface pressure perturbation is negative. That means the column is warmed, and you want to take that into account, and that adds to the potential intensity. There's a whole derivation behind this, but I want to focus on the actual observations, and they support this general idea. That's just showing you what these terms are. If you're interested, we have just finishing a draft of a paper on this. I'd be happy to pass it around. So I mentioned the 4 canonical storms that are given local names around the world. I'm first going to talk about polar lows. Historically, they were the first that you recognized as something special. And it's very interesting history because they occur, as I said, in the middle of the winter, not in the summer, when hurricanes happen. And they occur over water which is barely above freezing. So the weather forecaster said this isn't a tropical cyclone. It's obviously not tropical, right? Got that part right. But it is a tropical cyclone from a physical standpoint, and they look like. That's highs. I'm going to show you that. Here's a satellite picture of one in 1987, just north of the coast of Norway, between Norway and Svalbard. You know, see the nice circular eye, something like an eye wall around it. And they arise very quickly. And back in 1987, they were not forecast well at all. So they caught fishing boats by surprise. You know, 1 hour they're sailing nicely in clear weather, and 2 hours later it's terrible, and these ships would be sunk. So there was a motivation to try to understand, but they really are the same as hurricanes, except that their potential arose locally and suddenly rather than being there all the time. So here is a map showing at a particular time on the left the distribution of surface pressure, the conventional thing you see on a weather map, a little L showing a minimum, and the tight distribution of isobars around that indicate strong winds. That's how the polar low appeared in meteorologists' ERA5 analysis. And the right-hand map at the same time is the geopotential up in the upper troposphere. So for those who are not meteorologists, it's very similar if we took a plane surface and just calculated the pressure on that surface. Instead, what you're showing is the altitude of the surface, constant pressure, but they map very closely into each other. So you can see that almost co-located with the surface low is the big upper level cyclone. That's synoptic scale. That was the parent of this child, polar low. That developed over a period of 3 or 4 days. Again, from a meandering jet stream, cut off. There was all this lifting of the air in the troposphere, which created a cold pocket. This chart simply shows, at this time, the distribution of sea surface temperature of the polar center. Okay? So you can see at the bottom is the northern coast of Norway, and all that blue is just sea ice. In other words, on this particular map, at this particular time in 1987, sea ice covered almost all of this region of the Arctic. But there was open water in this area between Norway and Svalbard, as there often is, more so today than back in 1987. And it was over this pocket of relatively warm water that the Cyclops developed. And this map shows this modified potential intensity. What I'm not showing you is the potential intensity here, even over the open water, is usually zero. Literally zero. There is no potential. Only in this particular weather system, locally created this potential as evidenced by it. So theoretically, if everything was perfect, you could have a cyclone with surface winds of 50 meters per second. Now, in this particular cyclone, it didn't get to be that strong. It was more like 40 meters per second. But it's still, you don't want to be out in a small fishing boat in the Arctic Ocean with winds. The air temperature in the Cyclops, even at the surface, was well below freezing. polar lows is that thermodynamic potential is mostly recognized as an actual temperature difference between the water and the air. The water can be 7 degrees C, the air can be -3 or -5. And very dangerous for fishing boats because you get terrific winds, it lifts a lot of spray, and then it super cools and freezes onto the rigging of the boat, and the boat becomes top-heavy and capsizes. It's very, very bad situation. Here is a completely different polar low over the Sea of Japan. Okay, they're very common there as cold air flows off the coast of China. This one was back in 2009, which is like a small hurricane. People are used to looking at satellite pictures. And again, the left-hand chart it says 150 G of potential is the physical height of the surface of constant pressure close to the actual Earth surface. If you think of it as surface pressure, it's almost the same. And you can see the local minimum over the Sea of Japan. And right above it, a cutoff low. I should say for non-renewables, normally at this place, at this time of year, those ice bars would be straight lines across the map, showing a very strong west-east flow, jet stream, if you will. This has created a big meander, and that's all you're seeing in this local chart is that meander cut off below. It's called center, and that's what's created the geopotential. So there's the modified geopotential. At this time, the L marks the position of the polar low. And on the right-hand side is the quantity I haven't shown you yet, which is the relative humidity. The other requirement to get this kind of storm, for reasons I don't have time to go into, you have to have a humid middle troposphere. And that's often not satisfied in the tropics, which is one of the things that limits the rate of formation of hurricanes there. The lifting of the air that cools it locally also makes it humid. And then this is just the climatology of polar lows in the Sea of Japan. They're quite frequent there, and they can produce very, very heavy snowfall along the northwest coast of Japan, which is known for its very heavy snows. The second example of this kind of event are metacanes, closer to your location, presumably to your heart. And here is the photo, a satellite photo of a metacane in 2005 between Libya and Crete. You see it there, it looks like a tropical cyclone. It is physically the same thing. And if we look at the surface pressure, here's the analyzed surface pressure on the 14th of December on the left, 2005. And again, here's the upper tropospheric pressure, if you will, of the geopotential 400, showing a co-located low. Now, I should mention to you that with ordinary cyclones, which we'll experience tomorrow here, this is not the case at all. The pressure in the upper troposphere is usually just showing a kind of a trough, which is not co-located with the surface low, but almost always some hundreds or even 1,000 kilometers to the west. It's completely different physics for that kind of system. There is the modified potential intensity on the 14th of December on the left and the 15th of December on the right. And you can see that it has become less over one day, and we believe that's due to the heat flux from the storm itself, warming or rewarming this column of the atmosphere, thereby reducing this thermodynamic potential. This next chart is meant to show a problem that we have in looking at analyses of this. I've been showing you an analysis, and for the non-neurologists, I haven't told you what it is. How do we make an analysis of the atmosphere on a day-to-day basis? It's actually quite sophisticated. It's an exercise in state estimation. We start with a prior. And the prior was yesterday's forecast. That's your best shot at what it is today if you have no other information. And then we assimilate all the observations we have, aircraft, weather balloons, satellite information. It's a very sophisticated thing. In practice, that assimilation takes as much time on the computer as making an actual forward forecast. That's how much math goes into it. But the models get some things wrong, and when there's no data to correct them, you will get a bad analysis. And this shows, so on the left, we have an estimate, well, we have a measurement of the column integrated water vapor on the 14th of December from satellite, and you can see yellow there. This is not relative humidity, it's actually the actual column integrated mass concentration of water in the atmosphere. And it's pretty high, where this Mediterranean cyclone was at the time. On the right is the official analysis, or re-analysis of that, which shows some overlap, but really quite different. And the moral of the story is that even today we struggle with getting humidity of the atmosphere right in forecasts and analysis. Because over the water, we don't have very good observations of water vapor still. Okay? That's a lot packed into that. I'm showing you this is a big limitation on forecasting both tropical cyclones and this kind of cyclone. I haven't told you exactly why. The mid-tropospheric water is really important. It's important to be very humid, and we aren't being very good at either forecasting or analyzing that state. So it's a bit of an aside, but an important one. Here's another hurricane. Isn't that beautiful? Which is like a hurricane just to the southeast of Sicily and Italy in 1995. And this was quite well known at the time. Here it is the next day. You can see a satellite picture on the left. And there is the infrared picture on the left and the corresponding visible image on the right. And it had pretty much dissipated off the northern coast of Africa's Tunisia the next day. So these are short-lived, partly because they gobble up this potential pretty fast. Here's the surface pressure when the storm was just off of west of Greece, southeast of Italy. So very tight, concentrated minimum, and it formed, as they all do, in the back on the right-hand side, under an upper level cutoff cyclone. They all do that. This does not mean that cutoff cyclones invariably produce Cyclops. They don't. But the converse is true. You don't get them without that. And let's look at the evolution in this case. So on the top is the upper troposphere pressure distribution, or for the meteorologists, the 400 hectopascal G potential. On the bottom is the near surface pressure, or 950 G potential. So we're going to go in time from left to right and pay attention particularly to the upper row. You can see the formation of this cutoff cyclone. It's what we refer to as a Rossby wave breaking event, and it transfers a lot of kinetic energy into potential energy. And as that happens, a broad surface low develops. By the 15th of January, you've got a real Cyclops in the tropics. This is just giving you some feeling for the evolution of the atmosphere prior to and during the development. And here is, for the same period of time, the evolution of this potential intensity. So on the 12th of January, normally at this time of year, there is no potential intensity anywhere in the Mediterranean. But as this cutoff is forming, you begin to see some potential arising in the Adriatic. And as you go to the 13th of January, it's cutting off to the southwest. So it expands and amplifies. And by the 14th, you see a large section of the middle Mediterranean has potential intensity of 70 meters per second, which is like tropical hurricanes. And it's precisely there that the Cyclops developed. It's something that looks just like a hurricane. So, you know, if they say if it looks like a duck and it quacks like a duck, it's probably a duck. And then you can see this continued expansion and slight diminution afterwards. Third example, subtropical cyclone. Here is a cyclone over Gulf Stream in the middle of winter, January 2023, just southeast of Nantucket. This is not a place and time where you expect hurricanes to develop, but there is one. That's a cyclops, lots of convection in the center, the eye starting to form. Surface pressure, upper tropospheric pressure, same old, big cutoff cyclone, moves down over very warm water for that time of year, the Gulf Stream. And here's the modified potential intensity. The L shows here where the surface cyclone is located. Quite high values, and up in hurricane territory. But transient, again, normally 0 at this time of year. And finally, the Kona storm. Here's a picture of one. You see that little cyclone off to the left there? That's about 500 kilometers west of the islands of Hawaii. Okay, and they occasionally rise. Middle of winter. You're getting bored with this, so am I. You're seeing the same pattern over and over again. There's the surface low on the upper panel and 400 hectopascal potential co-located. And there's the modified potential intensity with the surface low marked there, quite high, 180 meters per second. The bottom panel is the same, but showing the climatology, the normal state of potential intensity. And there's a big gradient. As we go equator to Hawaii, as it's true for most of the tropics, there's just always a lot of potential there. There's not enough. Conventionally, you should have more than about 40 meters per second of potential intensity to get one of these storms. It doesn't quite make it climatologically, but you can see how different it is when the cutoff low develops and creates this. In fact, there's a diagram showing the anomaly away from climatology. 40 meters per second is a lot of anomaly. So these upper cutoff lows are really ideal embryos for hurricane-like development. They create the potential that allows Cyclops to develop. They also create an atmosphere with very little wind shear at height, because you're in the middle of the cyclone, right in the middle, there's no change in the wind with height. And it's humid. And both of those are other conditions you have to get this kind of storm. The normal state of the atmosphere where these things develop is unconducive for development of these storms. But the approach of this upper level potential vorticity anomaly, sorry for the acronym, and within the term itself, leads to lifting and cooling, moistening of air mass. And that very strongly enhances the thermodynamic disequilibrium between the atmosphere and the water. So that's just a repeat of this modification, and I can't remember why I put this slide in a second time. Oh, quantitatively, sorry, the boxes didn't come through. They're supposed to be approximately equal to signs, okay? So in this case, this is the Medicaid in January 1995. The perturbation at maturity of the potential, geopotential 950 was about 1,500 meters squared, second squared. The normal, or the conventionally analyzed potential intensity squared was 1,200 meters per second squared. Therefore, the modified potential intensity is about 15 meters per second. You can see that the modification is non-linear. Without it, we don't have enough potential to form a cyclone. One last thing, I don't know how I'm doing my time, but I'm getting close to finishing. Am I all right? Am I all right for time? Okay. We have, in fact, some time ago simulated these storms numerically with a model that is axis-symmetric. And so we insert the cutoff low in the initial condition into an atmosphere that has no potential intensity to start with. Insert a typical cutoff low. So the initial environment, and indeed the far boundary, which doesn't support any kind of surface flux-driven cyclone. We insert a cold upper low with no surface winds initially, with a maximum wind speed of 20 meters per second. Fairly weak, actually, for a wintertime cutoff low. At 300 kilometers radius and 10 kilometers altitude, just insert that, like the atmosphere did it for us, but we're providing it as an initial condition. And it's a very high resolution axisymmetric model that has been used for decades to simulate hurricanes with 3 3/4 kilometer horizontal resolution, 300 meters in vertical. So what you're seeing in this slide is radius from 0 at the left-hand side to 200 kilometers at the right, altitude in kilometers, and then the contours are the azimuthal component of the wind. And so what you're seeing, and this is a day 1, so it's not the initial condition, it's a day later. Mostly what you're seeing is the upper level cyclone, that red, which indicates cyclonic flow around the left-hand axis, that we inserted as an initial condition. This is balanced, it has cold air at the center, it's in thermal imbalance. And on the right-hand side, we see the temperature progression from the initial condition, or from the unperturbed atmosphere. So it's a cold core cyclone in the troposphere, of course, a warm core in the stratosphere, because the wind goes to 0 at the top of the domain. So we're just going to watch the evolution of that in the model, that field. That's what I just showed you, day 1. 1 day later, a much smaller scale cyclone, which is only 40 kilometers, has formed inside this large synoptic scale embryo. That's the Cyclops. Okay. It formed in response to the fact that you have a lot of thermodynamic disequilibrium once you put that cutoff level. So that just develops over time. You have the usual collapse of the eye wall into a discontinuity or a near discontinuity. Notice the strongest winds are now on the surface, and notice that the winds aloft have decreased appreciably from the initial condition. I'm going to play the sequence rapidly on the That's the daughter or the child below eating its parent. Okay, it's warming up the column and destroying the upper level cyclone that gave rise to it in the first place. I was joking with Paolino for lunch, it's like a black widow spider. Not quite. It's and there it is a day later. Okay, so now after day 5, it looks just like a numerical simulation of an actual tropical cyclone, with hardly anything left of the upper level cyclone is turned into day 6, day 7. So I'm just going to play the whole sequence one more time for you, starting there, and just go through it. That's the initial condition with no wind at the surface, quite the initial condition, and a strong upper low, and there it goes. Okay, so we try to unify these disparate phenomena that have regional names all over the world. They also occur in the southern hemisphere. I should show a southern hemisphere example. I don't know why the northern hemisphere. We christen them Cyclops, which means an acronym for cyclones from locally originating potential intensity. And they form, by definition, these climatological mean states that are at best marginal for surface flux-driven development. Often, there's no potential at all to start with. And that can be either because the potential intensity is too small or the atmosphere is too dry. The approach of this, the development of this upper level cutoff cyclone converts kinetic to potential energy and lifts the troposphere and cools it, and also raises the relative humidity. Increases the potential intensity and reduces wind shear, all of them conducive to this sort of thing. So the troposphere underneath this kind of system over the ocean can be an almost ideal embryo for incubating these hurricane-like storms. And you can read some more about the effect of climate change on Cyclops on the paper residual developed at Acme by my colleague Romu Romero, who is a professor at the University of the Balearic Islands. And so that water flood risk for Cyclops. So we're now going to take the science and try to turn it into long-term estimates of risk and start in the Mediterranean region. So thank you very much, and thank you to those of you who aren't meteorologists for being patient.
So, who wants to be the first to break the ice? To make to ask some questions, especially.
Thank you, Kerry, for this presentation. And I always have some, when I see the levels, so like 95 hectopascal, 400 hectopascal, I always wonder why we choose that level, and if there could be some like universal scaling for this level across all the sizing. For example, let's say I will dimensionalize with respect to lifting condensation level or some level which is well known in the dynamics. And I've seen that always regarding the formula, the new formula, and there are 5 different contributions, but what I've seen, and I want just a confirm about this, is that the most important is the geopotential perturbation term. So
That's right.
the other comes from the theoretical analysis, right? The SST and the 400, but the geopotential term is the most important.
So there's a potential for confusion here. When we think of 3 states, the unperturbed state where you don't have a cutoff flow. In that case, in most of the examples, I'll show you there is no potential density. Cutoff flow develops, and let's, just to make life simple to discuss, say a cyclops hasn't started to develop yet. That isn't correct. They usually develop, not exactly together, but pretty closely the same. But let's suppose it hasn't developed. Then there will be a lot, if you look at, say, the ERA5 reanalysis or any reanalysis, there will be a lot of potential intensity there. And that's calculated from the standard algorithm, which depends only on the ocean temperature. Basically, you have to give it the whole temperature structure in the atmosphere about that. There's no assumptions about this level or that level. You just get a potential intensity. And if the cyclone hadn't developed, you'd stop there. And you say there's a lot of potential for a cyclone to develop. And you give it to the forecaster. The forecaster looks at that and says, maybe we're going to get a cyclone there. You look at other things too. The problem that with this perturbation that you're talking about is that when we look at the analysis, it already typically has a cyclops in it, if we're looking for cyclops. And it has warmed the column, and therefore eliminated some of that potential intensity. We're trying to correct for that. So in that equation I showed you, the unmodified potential intensity is not the climatological one, which is 0. It's the potential intensity we calculate from the sounding in the reanalysis. And it only depends on that. You don't have to make any assumption about levels. But the modification is the modification produced by the cyclops. You're trying to use the surface pressure perturbation as a proxy for the warming of the column. And I can give you the math.
Yes.
And so in that case, right, usually they're both contributing a lot. Because the first term on the right-hand side is not completely unperturbed. That's what you get from the reanalysis. But it's been contaminated by the presence of the cyclops. So it's a little involved, but that's what's going on. You mentioned in your first question about why did I choose 400. The 400 never enters any of the calculations of the modified potential intensity, set for the absolute temperature. It's supposed to be upper troposphere. But whether it's 300 or whether it's like 220 or 230 or 240, you're taking the ratio of that seasonal temperature. It's not very sensitive to what you choose. It's a little arbitrary. It's just meant to be. That's the only place in the calculation at 400. And if I use 500 or 600 or 200, it wouldn't make much difference. But the fact that I use 400 millibar charts was an arbitrary choice, but just to communicate to you through mass what the upper troposphere looked like.
Yes, okay.
Yeah.
Okay. Well, I also... Yes, no, go. I will do this.
My question, a couple of questions. Thanks for the presentation, Prof. I appreciate it. Regarding the structure of these cyclones, do they rotate? Do they show always the same sense of rotation?
They do.
Okay.
They all do, and it's anything that lasts more than a small fraction of a pendulum day. By the time it takes a pendulum day, it's going to be in the atmosphere strongly influenced by rotation. So these are on the time scale of 12, 24, 36 hours. So they all rotate counterclockwise in the northern hemisphere, clockwise in the south.
Okay.
You get down to the scale of water spout, and it's arbitrary. You're talking about arbitrary vorticity that has little to do with Earth's rotation.
I see. From a thermodynamic point of view, have been this object analyzed in terms, entropy production? If this object have been analyzed under the out of equilibrium thermodynamics point of view?
They have, yeah. They're fascinating because the whole entropy budget of the atmosphere is something that is mysterious and fascinating. If you look at the global irreversible production of energy by the planet Earth, does anybody know where you're going to get it wrong? Okay, for sure. But go ahead and be bold. What's the main source of entropy production on the planet Earth? In other words, if you look at photons leaving the planet from the ground, they're carrying more entropy than the ones coming in. What's generated?
Friction.
So if we didn't have any, this is going to give away part of the answer, but we didn't have any water in the atmosphere, it would be friction. But it isn't. It's way down. It's like number 8 on the list of processes, friction. It surprises the heck out of me. Anybody want else want to take a shot? I'm giving you a clue by accident.
Water vapor.
The ocean. Yeah, the ocean is actually a minor player in entropy production. That's another surprising thing. The velocities are very small, even though the densities are high, and there's not that much trivial dissipation compared to the atmosphere. So I've already said that frictional dissipation in the atmosphere is small, oceans even smaller than that. It's irreversible mixing at cloud boundaries. You know, when a cloudy, moist air mixes with dry air, that's an irreversible process. That wouldn't surprise you. What would surprise you, surprise me, is that's the main chunk on the whole planet. Anybody for a second? Second most important.
Condensation.
Yeah.
That's usually very close to reversible in the atmosphere. It's frictional dissipation of falling raindrops. They fall down, they're falling at terminal velocity, they're dissipating gravitational potential with the heat. It's the second most important source of energy. So we begin with that as a backdrop. Hurricanes are special because when you have a really strong hurricane that's operating perfectly at Cat 5, there, locally, it's almost entirely frictional dissipation. And it's because the whole atmosphere is humid, so there's not much internal irreversible mixing. The rotation inhibits lateral mixing. So it is nature's way of basically responding to the fact that as you raise the temperature, you are, of the surface, you are exporting more entropy into space. It can't all be taken up with this binary mixing mechanism. So nature has developed a second way of doing it. That's one thing. if you want to look through the entropy lens, that's one way to look at it. Kind of fascinating.
Thank you.
I promise not to get the wrong way to answer the question.
Kerry, you mentioned 4 examples of cyclops, and you were saying that everything is connected to the climate change, and you said that to have cyclops you have to be far away from the perturbation around, so it must be something local. What is the difference between, in terms of distances, in this, for example, you did between hurricanes on the Mediterranean, polar lows, and tropical effects?
Yeah, they're all very similar scales. They tend to be a little smaller when we get closer to the pole.
But they must be distant in a different way from other examples.
Yeah, I mean, think of just ordinary cutoff loads on weather hubs. It's basically where do you have those and how they grow. Pretty much.
Whatever question we have on atmosphere.
I have a question about the discrepancies of the total precipitation of water from the analysis from observations.
Yeah.
So to what extent this difference affect the estimation of the potential intensity based on the analysis? And how the observations could be used to prove?
So I'm going to repeat for the sake of the recording the question, which is how does the analysis of column water vapor affect the potential intensity and so forth? It actually has almost no effect on the calculation of potential intensity, but it is another completely separate requirement to have a surface flux during the cyclone, that the column that occurs in has to be almost saturated. And it gets back to your question. If not saturated, all that entropy production that comes from, would come from the carbon cycle, gets used up in mixing across water vapor gradients, and there's none left over for friction, if you look at it that way. So this is both observational and strongly theoretical, where both agree you have to saturate the column. And I skipped over that one. But if you get that wrong in the forecast, you can have a perfect potential intensity. That's the easy part. Getting the water vapor is hard, and the observations are not great. Satellite is okay for column water, but not for its vertical resolution. We don't usually have balloon soundings. And airplanes don't land and take off over the ocean. It's not normal. And, so we don't have a lot of data. And then the models do what they do, and they're not usually right about water vapor. It's a big problem.
So in the formula of the potential intensity modifier, you have this term where you have the ratio between SST and the temperature at 400 hectopascal. So when you have a one core cycle, that ratio decreases.
When you have a
one core cycle.
True.
So the term on the right side of the equation decreases of solution, increases the potential intensity.
The modified one, yeah.
Yeah. Okay.
It can do that. There's a problem, not conceptually, but in terms of actually trying to calculate that. First of all, the Fourier mill bars is, as you pointed out, in that case, arbitrary. It's somewhere up there around the level at which the pressure perturbation of the Cyclops vanishes. It's going to be somewhere up there, but not. Also, CK over CD, I never talked about that.
Yeah.
That's the ratio of the non-dimensional scaling coefficient for enthalpy of the sea surface to the drag coefficient. It comes from the theory. We know exactly what those are on land, we know the surface roughness. We don't have a clue what over the water under high speed wind conditions. So my inattentiveness to that temperature is a refusal to look for the keys on the lamppost or the problem somewhere else. In other words, we don't know cicada or CD anyway very well. So why bother too much? So we don't know that coefficient all that well. It's probably going to be between 1.2 and 1.4, somewhere in there. So yeah, if you really want to calculate that well, you have to pay more attention, but you also have to solve some outstanding problems. And this is a big problem for hurricanes, is all the flux is coming at the eye wall where the winds are 80 meters per second, and there is no sea surface. You're going from bubble-filled water to spray-filled air in a continuum. It's an emulsion, and we don't know how to calculate heat flux through an emulsion at high wind speeds. It's a completely unsolved problem. We try laboratory experiments, they're fun, and you get wet. We haven't learned very much from them. We've flown airplanes in expressly try to get that as a budget as a rule. Nothing has worked with that huge error bars. So, yeah, we have a lot of problems to solve stuff.
What about the frequency of these different examples you give?
So the climatology of the Mediterranean is on the average 1.5 per year. Okay. Well, Mediterraneans. And the climatology is more for the Sea of Japan, but I don't remember the numbers. Thunderstorms, maybe once a year.
Yeah.
Thunderstorms, we call things that we would not call cyclops, are also called cone storms out there, so that's the way.
So they are extreme events.
They're extreme events.
And this regular occurrence of these events is because cutoff are not rare. So the point is that they have to be aligned with the sea surface temperature. So in the alignment stands the rate of occurrence, the small occurrence of these.
Well, they have to occur in a region where the potential intensity isn't otherwise too negative, otherwise overcome with this. The cutoff is a couple of things about the cutoff. It's a reflection of the fact that you're locally converting kinetic energy, jet streams, if you will, into potential energy. That has to happen. It could maybe take forms other than a cutoff. I don't know. That's a sure sign that that's happening. Also, you have to create this humid column, which is very important, although I didn't emphasize it. Also, the fact it's cut off means that the center there's no vertical wind shear. And wind shear is, especially if it's accompanied by dryness of the troposphere, will wipe out any type of cycle. So that's why it's important. If you just have a deep trough, it could be cold core, but you have a lot of wind shear.
So I have a question connected to that one. So basically, I don't know if I'm getting it right, but all these cyclops, for example, the Medicines, if these two conditions aligns, you can get like a tropical transition. So, okay.
Yeah, if that condition happens, you need the humidity, you need the local potential density,
Yeah.
and you need the absence of wind shear.
Okay.
Now, the question that's unanswered is those three things constitute just a necessary condition or are they also sufficient?
Yeah.
That remains to be seen. It would make a good thesis.
But so a follow-up question that you didn't talk about your Genesis index,
No,
but did you already try to put your new potential intensity inside it?
I haven't done that.
Okay.
Good idea though.
Yeah. That's
The problem is I don't know if I trust the humidity from the analysis. So that's
Yeah.
a big factor in that. I trusted that I put it there.
okay.
It would be nice to speak about the climate change and the effect on the cyclops, but it's not the case now. Okay. Anybody has any question about this? Okay.
We're going to let
Yeah. Nah.
Hopefully that nobody from the US and the CDC will stop.
That's right, you have to filter that out when you pass out. No Americans can get them in the car.
I don't
I
know.
said climate once or twice.
It's also there up in the summary.
It's
So.
actually not fun. No one can laugh.
Unless
Ah.
we can talk about what we know about climate change. So it's very interesting what this.
Yeah, I don't know if I'm going to